Good morning, good afternoon, good evening, wherever you are joining us from. I'm Jenny DiFigueredo, the Community Manager for DVC. We've got a really interesting use case today to help you productionize your LLM projects. Sharing this use case is Joschka Braun. After completing his Master's in Science and Math at NYU on a Fulbright scholarship, Joschka started researching applications of deep learning to medical imaging at Covera Health. After that, he built multi-modal semantic search systems and automatic code generation software at Jina AI. Last summer, he participated in Combinators S23 batch and co-founded Parea AI, an SDK and platform for testing, collaborating, and monitoring LLM apps. Today, he will be sharing how to combine Parea with DSPy and DVC to achieve production-level performance in your RAG projects, something we all need. So our tech rehearsal was great. So be ready to take notes and ask questions. Feel free to put your questions up in whatever platform you're joining us from right now, and I will be facilitating those to be answered throughout the presentation. So with that, I turn the floor over to Joschka.
Amazing. Yeah. Thank you so much for the introduction. All right. So I will be first talking briefly about RAG, just reminding, I guess, or like give a brief refresher. Then I will be talking about what DSPy is and talking about the key ingredients. Then I'll be using DSPy to first define a naive RAG system and then a multi-hop RAG system. And finally, I'll be talking about how DVC helps in that entire process of experimentation and evaluation. So retrieval augmented generation consists first of a retrieval step. And this could, for example, look as the following diagram below. We have some documents, and then we use an embedding model to embed those documents and store those vectors in a vector store, which could be as simple as a NumPy array. And then a user comes in with a query, and we use the same embedding model to also embed this query and find related documents among these documents, which we indexed earlier, to retrieve a context. And the second part of RAG is the generation step. So now we have the relevant context for our query or for our question, and then we will feed the query together with the context into a prompt, which we will use to instruct an LLM to generate a final answer. That's just very high level RAG. Now about DSPy. DSPy is an acronym for Declarative Self-Improving Language Programs in Python. And DSPy is mainly based on a similarly named paper, which got published last October. And the associated GitHub project or repository got a lot of traction like during that time, like around like 4,000 GitHub stores, but it only became more mainstream like earlier this year in January, February, and has now reached more than 10,000 GitHub stores and has a very active Discord community. And what DSPy allows you is to define an LLM program. And you only specify essentially the flow of your program without worrying about the low-level details, such as how do I actually prompt the model correctly? How do I choose the correct few-shot examples? And it does that by optimizing every step of your pipeline. So once you've used DSPy to define your flow of your program, you can then use DSPy to jointly optimize every step of your pipeline, which means like the instructions, the LLM weights, etc. And to really understand how this works, I will be introducing three key ingredients, which is signatures, modules, and optimizers in DSPy. And the first part, signatures, they are describing the input and output behavior of a DSPy module. But then not only describe the behavior, but they really control the behavior of what is happening within that step, essentially. And to see a concrete example, we can think back to the answer generation step in our RAG pipeline. So for that, we would introduce a signature called generate answer, give it a doc string, which says answer questions with short factored answers. And then we specify two input fields, the context and question, and then instruct the LLM to generate the answer given those two inputs. And we will see that in a moment in action, actually. But before that, we need to talk about modules. And modules in DSPy are the composable building blocks which define your DSPy program. And they're very similar to PyTorch modules in the way that you first have to specify a constructor where you specify every layer of your DSPy program. and then you write your forward pass. And in that forward pass, you specify what is actually happening within that LLM program, essentially. And DSPy also comes with built-in modules, which abstract away certain prompting techniques, for example, chain of thought. And if you think again about this PyTorch analogy, PyTorch also comes with built-in implementations of 2D convolutions. To see, for example, such a built-in DSPy module in action, we can use our chain of thought module and apply the generate answer signature on that to create this pipeline, and then use that to answer questions about OpenAI. And we can see that the prediction for when was OpenAI founded was December 2015. And what actually happens under the hood when we define this chain of thought program with our generate answer signature is that during this forward pass here of a chain of thought on question and context, actually a prompt is formatted or constructed under the hood. And concretely, the chain of thought module with the generate answer signature will take the doc string of our signature to start our prompt. So it will write answer questions with short factual answers. Then it will describe the actual format and how the LLM should respond. And for that, it will take all the input fields we have specified, so context and question, put them here with their respective question description if given. Then the chain of thought module introduces another field, which is called reasoning. And this will just instruct the model to think step by step before answering. And then it will instruct the model to give the actual answer. And then finally, during that forward pass, it will fill in the question and context at the bottom of the prompt, and then let the LLM generate the rest of the answer. And that's how the previous answer, which we saw here, came about. But we cannot only define use these pre-built modules, but we can also define custom modules, which are very interesting. So if we want to define a RAG pipeline, we can just define our RAG module, in which we overwrite the initialization function and pass in the number of passages or context we want to retrieve at every point. And then in this initialization step, we will first use the DSPy built-in retrieval mechanism, and then the chain of thought generate answer signature to generate an answer. And during the forward pass, given a question, we will first retrieve the relevant passages, and then we will generate a prediction with our chain of thought pipeline, and then return the context as well as the answer. Then to see this actually in action, we need to instantiate our RAG pipeline, and then we can just ask a question of when was OpenAI founded. We can see here some context got retrieved, some of that relevant, some of it not relevant, but we see the final answer is 2015, which matches what we saw earlier. So we now know signatures and modules in DSPy, which help define essentially our pipeline of our RAG system. But then the last key ingredient which we need are optimizers. And optimizers, they take a training set and an evaluation function and optimize all the parameters of our DSPy program. And this means it will either optimize the LM weights if it has access to it, or it will refine the instructions. So I'll think about the doc string we had earlier in the generate answer signature, or it will select few-shot examples which improve the performance of our program. And DSPy comes with various built-in or predefined optimizers, which basically take away all this hard work of defining them. And one example is the Bootstrap few-shot optimizer. And this one takes the actual pipeline to generate few-shot examples and then selects those which have a really high score based on our eval metric, and then adds them to the prompt to steer the model in the right direction. Then another optimizer is CoPro. And this optimizer is refining and iterating on all the descriptions and doc strings and of our signatures to basically refine the instructions of what the LLM should do at every step. And then finally, we have a Bootstrap fine-tune optimizer, which fine-tunes an LLM for every step. And this is really helpful if you want to distill the performance of a prompt-based pipeline into a LLM-based pipeline, we have like access to a local LLM, which is then much smaller and costs a lot cheaper. So to recap on the key ingredients of DSPy, we have signatures. They not only describe the behavior, but also really control the behavior of our modules. And it's very much, so I would think back about the input and output fields which we specify. Then the key ingredient are our DSPy modules, and they define the flow of like, how do we actually execute every step of our DSPy program. And they're very similar to PyTorch modules. And then finally, we have an optimizer, which then either refines the instructions or selects future examples or just optimizes LM weights. So now we have like some understanding of DSPy. We can actually use it to look at a naive RAG system in it, or based on that. And actually, when introducing our RAG, when introducing DSPy, we already defined a naive RAG system. So if you at the bottom, the class I defined earlier with the forward pass, we first retrieve some context, then generate a prediction, and this is all based in the generate answer signature. And to understand how good our naive RAG system is, we're going to look at the Hotpot QA dataset. And the Hotpot QA dataset consists of more than 100,000 samples based on Wikipedia. And the interesting part about the dataset is that it requires, or that the question requires reasoning across multiple documents to generate an answer. And as well, this dataset comes with labels for the correct documents, which should be retrieved at every step. And we'll use GPT 3.5 Turbo as the LM, which powers everything, and just select a random subset of 50 samples of that data set. And to evaluate that, we will use Parea. So for that, we first need to instrument our DSPy program with Parea, which just amounts to those 2 lines. And this will give us visibility into what happens at every step of our RAG pipeline. So what goes into the retrieval step, what gets fetched, which context gets fetched, and how does the answer actually gets generated. And then the second part is evaluating this DSPy program. And we do that by just defining this experiment, giving it a name, a test set in the RAG pipeline. And to this RAG pipeline, we also attach 2 evaluation functions. One is answer exact match, which measures if the answer of the RAG pipeline matches the answer given in a test set. And the other eval metric is gold passages retrieved, which measures if the actual correct documents or Wikipedia articles got retrieved to answer this question. And when we execute that on the naive RAG pipeline I showed earlier, we get the following overview. So this is a screenshot from the Parea pipeline or from the Parea UI after running the experiment. And we can see here that the answer exact match has an accuracy of 56%, which is kind of okay. But what's really worrying is that we only have 26% in the correct passages retrieved. So this means that even GPT 3.5 Turbo just memorized like a lot of the answers without being reliant on the actual context retrieved. And to solve that issue, we're going to look at a multi-hub RAG system. So it's essentially, you have a course corrector and retrieval step. And what this exactly means, I will show in a second. But first, I want to look at an example to motivate that system. So here's another screenshot of the Parea UI. In this context, this is the observability part. So we can see here on the left side a hierarchical overview of all the different steps taken. So we see here the entry point is our RAG class. We have a retrieval step, which uses Colbert v2. And then we have the chain of thought answer generation, which uses GPT 3.5. And the middle part contains the input, output, and target or reference answer for that step. And on the right side, we can see things such as latencies or any kind of scores. Making this a bit larger and taking a look at the question of what city is 11 miles north of the birthplace of actor Toby Sawyer, we see that the answer exact match gives us a score of 1. So the answer matches the golden answer, but not the right passages were retrieved. We only retrieved information on the Sawyer family, but not an actual Wilmslow, which is where Toby Sawyer was born. So if we take a step back, I would solve this problem by first looking up Toby Sawyer, so that's good. But what I would be then doing is actually Googling for Wilmslow to understand what city is 11 miles north of that. So we want to have a system which dynamically generates more questions based on the context we already retrieved to then fetch more information necessary to answer the final question. And this can be encapsulated in a multi-hop retrieval system. And this looks as follows. We have a question, which is just given. Then, for example, what city is 11 miles north of Toby Sawyer's birthplace? Then based on that, we generate an initial query. With this initial query, we retrieve some passages, add them to our already retrieved context. Then we check, did we already reach our max hops? So in the previous example, I would be taking 2 hops, but here it's just a parameter which we specify. If we didn't hit that limit, we just go back to generate a query, and now we generate a query based on the question we have and the previous context we fetched. And the idea is to generate more queries, which then retrieve the missing information to answer the actual original question. So we retrieve more passages, add the new passages to our context, and keep on doing this until our for loop is done. And after we have retrieved max hops of context, we have hopefully a very diverse context which helps us answer that question. And to implement that in DSPy, we need to first introduce a signature which generates this query here. And this looks as follows. We give it a name, generate search query, and the idea is that given the context and the question, we will then generate a query. And taking that signature, we can now define this architecture, which you also call a simplified Boolean. So we pass in parameters for the amount of hops we want to take, or like how often we want to basically generate new queries to retrieve more context. And then we also specify the amount of passages we want to retrieve with every hop. And once we have these parameters, we initialize max hops of layers, which are just chain of thought in a generate search query. We still use the same retrieval mechanism, and then we initialize our generate answer layer. To implement then the forward pass, we take the question which we get and initialize our already retrieved context to an empty list. And then we iterate max hop of times by first generating that query with the respective chain of thought layer. So this corresponds to this step here. Then given this query, which we see here, we retrieve the respective passages, which we can see here. And then we add the new passages to our context. So we deduplicate the combination of them. And then we check, did we already do max hops? If not, then we just continue that iterative cycle of fetching more and more context to have ideally very diverse context. And once we're done with that, we can just use our chain of thought prompt to generate the final answer. And that's just a simplified Boolean on a high level. Now we're actually in a position to optimize our entire pipeline. And we do that in this example by selecting the Bootstrap few-shot optimizer, which will give some evaluation metric, which will measure the accuracy of the answers, but also if the right passages got retrieved at every step. And then to optimize our simplified Boolean module, we just call the compile function on that optimizer. And this then results in the following metrics. So we can see here that our answer exact match accuracy got improved by 14%, which is now at 70%. But what's really good is that our retrieval step has more than doubled to 56%. And this was all just only based on 20 training samples, actually, which is very exciting. And that's an example how you can use DSPy to very simply define in your architecture without worrying about the actual implementations of like, how do I prompt the model? What few-shot examples do I select? And then you just give it a training set to then optimize the entire pipeline. And for example, the effect of this optimizer is that this was the original prompt for a sample to generate the answer. So we can see here the answer questions with short factored answers. We see here the format we specified, and then the actual field in context and question. And then the optimizers generate a lot of few shot examples, and which led to this very, very long prompt here, which has increased our performance. So we can see here a couple of few shot examples selected. So now we're seeing DSPy and how multi-hop RAG systems work. Then the next step will be DVC. And DVC is very useful to make experiments reproducible. And it's essentially, or its experiment tracking feature is essentially Git for experiment tracking. So this means that whenever we run an experiment, we have now a snapshot of experiment name, the metrics, and the associated workspace. So we can always revert our code to the state of that experiment and rerun the experiment, and we don't need to create extra Git commits, which would just pollute our history. And setting up an integration with Parea is very easy. So first you would run DVC init, which just initializes your DVC repository, and then you would run Parea DVC init. And with that, whenever we run p.experiment with Parea, we automatically track that experiment in DVC. And this then allows me to use my two most favorite commands of DVC, which is one, DVC experiment show, and that allows me to quickly compare all the experiment metrics since the last commit. And then also DVC experiment apply, which then allows me to revert the state of my workspace to that particular experiment. And to show it actually in practice, I have here just a small, basically a snapshot of the Google Colab, where we can see here the RAG module and then the p.experiment function. And then I can use DVC experiment show to actually show me all the experiments I ran. So you see here the naive RAG system got a 56% in answer exact match, and the unoptimized Berlin got 62% in the answer exact match. And if I then want to check out this actual experiment, I can just copy this text, write DVC experiment apply, and this will now check out this the state of the code at this point. We can see here the simplified Berlin. I can also look at, for example, the diff, which is now shown via Git, and can understand how did I actually change the entire code. And that's very useful to understand if I, for example, change the descriptions here, or have minute changes in the actual fields I'm using. So that's DVC and the integration with Parea. And then to conclude, I can say that DSPy makes it very easy to just focus on the flow of your program of your LLM program, without needing to worry about the actual prompts or how to fine tune a model. And then Parea makes it easy to debug and test every step of your DSPy or LLM pipelines. And then finally, DVC enables the reproducibility of all the experiments you run, so you don't need to worry about committing that particular state of your workspace to the Git version history. Yes, and that's it. Thank you very much for listening, and I think now's a good time for questions.
Yeah, for sure. Thank you. That was really awesome. We currently don't have any questions, so I have a couple that I wanted to go over because a lot of this is new to me, and I was also monitoring what was happening with everything else here and putting links and stuff. But I had, because the multi-hop thing is new to me. So can you explain, and you may have covered this, but what constitutes a hop? What is the beginning to end of a hop? And then secondarily, how do you know when you are at the max hops reached? Is that when you're getting the evaluation metric you want, or something else?
Yes. So the max hops is, you need to specify this when you initialize the system.
Okay.
So you could, for example, incorporate an eval metric or some LM judge to do that. But the simplest way is just basically specifying I want to do 5 hops or 2 hops.
Okay.
And a hop is just this one cycle of generating a query and fetching new context.
Okay.
And it's just a single hop, yes.
So it'd be if you're setting how many epochs you want it to run or something, essentially. Yeah.
Yes, exactly.
Okay.
It's a hyperparameter.
Okay, cool. And then the other question, since you showed DVC, and it came from the team also, was have you tried running the experimentation in VS Code yet? Because we have a VS Code extension that has, the table and everything. So it's not just in the command line, it's a little more full.
I'm using PyCharm, unfortunately, so I
Okay.
can't take advantage of that. But I saw
Yeah.
it in Docs, which is like very nice, actually. Yes.
Okay, cool. All right, we do have a couple questions that came up. So one is from Vikram. You mentioned DSPy module holds the weights. Can DSPy tune the LLM weights?
Yes, yes. So for that, you would just specify maybe like a local llama model, and then you can use this bootstrap fine-tune optimizer, which will then DSPy will optimize those weights. But for example, that's not possible, of course, if you're using GPT 3.5 Turbo.
Okay. And the next question is from Alex Hasha. Hi, Alex. It looks like Parea gives you observability on the prompt sizes, which would help manage costs. Newbie questions. Don't these complex multi-prompt approaches get super expensive?
Yes. So with DSPy, you will, as we saw, like we can end up with these very, very long prompts here, which can be costly. In this context, because we used GPT 3.5 Turbo, it's actually not that bad, and we can get very good performance without needing to use GPT-4. But the pricing is a lot cheaper, so it's totally fine to have these very long prompts. But if you're now, for example, using like GPT-4, then yes, it could become very expensive. But it's kind of like a trade-off you want to take between very high accuracy and cost. And once like you have high accuracy and also high cost, then I would start thinking about distilling this prompt-based approach here to a local model, which you can just host a lot cheaper.
Okay, cool. And then he has another question. Any best practices for balancing cost and performance with these tools? So yeah, I mean, I guess you just covered that. Like, yeah, start with the expensive and then cut it back. Okay, anything else you want to add to that?
No, I would first go for performance, and then afterwards, like try to like reduce the cost. And
Okay.
yeah.
Cool. Okay, next question is from Brett. Can I implement this on ARM processors plus GPUs?
That's a fairly detailed question. I'm not sure how well that is supported. I would check the DSPy docs on that. I haven't done it, so I can't talk about it.
Okay, fair enough. And from Salah, is there a way to observe the final prompt generated by DSPy, and what observation tools do you use?
Yes, so I use Parea for that to generate or like to basically find out those prompts. So you run this optimization, and then you would run this evaluation step, and then you will see which prompt got used in this evaluation step. So for example, the screenshot I took here, this is directly from the platform from Parea when I did inference and observed that.
Cool. And does DSPy work with an ensemble of the small LLM models?
Yes, they also have an actual built-in module similar to the chain of thought, which does this ensembling for small LLM models. So it's very nice for that.
Cool. Awesome. That is, oh, okay. We have lots of thanks and very neat. Thank you for answering the questions. But I'll wait a second to see if there's any other questions coming in. But if not, then I want to thank Joschka for being here today and sharing this amazing use case with us. It was fantastic. Thanks to all of you for being here with us today. And the next meetup that we have will be June 12th. It'll be Dmitry Petrov, our CEO. He will be presenting an LLM use case with our new tool, DVC X. And I put some links and all the things about joining our Discord server. If you have a use case that you would like to share with DVC, by all means, reach out to me. I am Jen DeFig on Twitter and Discord. You can reach out to me on LinkedIn. Good luck figuring out how to spell my name, but you'll find me if you started in LinkedIn. And also my email is Jenny with one N at dvc.ai. Thanks everyone for being here, and we will see you next time.